Hi everybody, welcome back to Chem 140 for the last week of classes. Hard to believe that we're already at the end, but here we are. What do we got going on today? We're going to finish Unit 15. I think we have to do percent yield or something like that. And then we'll move on to Unit 16, and we're actually a little ahead of the schedule, so we'll do what we can today for Unit 16. We might talk about the lab a little bit today. And depending on what happens, we'll talk about what we'll use tomorrow for. But we'll finish Unit 16 probably on Thursday, and then that'll be it. The last quiz will go up. Exam number 2 will be posted at some point. We'll talk about that on the last day of class. And then you have a final. So, lab worksheet number 4, which I assigned to you week 8. That seems like forever ago. It wasn't due last week because I think it was just an assignment that was more difficult than the others, so I had put it on the schedule to give you 2 weeks. So that's actually due this Thursday. So make sure you get that in by the deadline. And lab worksheet number 5 will have a due date next week during finals week. So, all right, so let's talk about percent yield. In the lectures last week, we talked about how to do stoichiometry by converting stuff to moles. Turning grams into moles is trivial. We've been doing that for quite a while now. Turning moles of something into moles of something else depends on the balanced chemical equation. We could do that too. And then if I give you 2 starting amounts, you can tell me which of those is the limiting reactant. Now what I'm going to do is I'm going to first open my seltzer water here because I'm trying to do it quietly, but it's being difficult. Now what we're going to do is talk about reaction yield, which is, okay, here's how much I expect I should get based on the calculations we've been doing. Here's how much I actually got. Are the numbers the same? Well, let's see. Now, it turns out that when we do chemistry, excuse me, not all reactions go to 100% completion. In fact, it turns out very few reactions go to 100% completion, and there are a lot of reasons for this. The most important reason of those is thermodynamics and equilibrium. So we're going to talk about that in 162 and 163. So equilibrium specifically is, hey, there are other reactions going on. One of those reactions is the reverse reaction of what you're trying to do. And that reverse reaction will always be occurring. And if you use up all of the reactants, there will only be products. And so the products will just turn back into reactants very slowly. Or very quickly, depending on the reaction. The other outcomes that affect your yield would be things like, oh, I did the experiment at a temperature that was so high that the product decomposed and I got something different than what I wanted to. Like maybe it became a gas and evolved or something like that. Or it could even be something like, oops, I spilled. In order to turn in my compound, I have to put it in a bottle and then put that bottle on your desk, and here it is. But in the process of putting it in the bottle, some of it spilled on the counter and I couldn't get that in there. Or maybe you dropped it on the floor and it went everywhere and you only got like half of what you dropped. So these are all things that affect your yield. Your yield that you produce is called the actual yield. It's what actually makes it to the end. So if you mix 20 grams of A and 20 grams of B and you create 5 grams of C, I don't know where the other 15 grams went, but this is the 5 grams you have to show me. That's your actual yield. You actually got 5 grams. Now, if we're doing the calculations on paper, the paper calculations are your theoretical yield. These are the yields that you're supposed to get if everything goes perfectly. And on paper, everything goes perfectly, because it's in theory. This is what you should get. You do the reaction. You react this many moles of reactant. You get this many moles of product. That's this many grams. So in theory, you should get that. But oftentimes, theory and reality don't match up 1 for 1. So that's where percent yield comes in. The percent yield that you get is just what you got divided by what you're supposed to get times 100. So if you got 5 grams, but you're supposed to get 10 grams, your percent yield is 50. You got half of what you're supposed to. Simple enough, right? Now, this is a formula, which means that of the 3 variables here, here's a variable, here's a variable, and here's a variable, I can give you any 2, and the third one can be solved for. So we'll be mindful of that when we solve these problems today. So let's do some. I'm going to react 4.7 grams of hydrogen with excess nitrogen. So this is not a limiting reactant problem. This is just excess nitrogen. And I got 12.5 grams of ammonia. What is the percent yield for this reaction? Well, let's find out. So if you're ever given a percent yield problem, the first thing that you should do is write down the percent yield equation. Okay, there we go. So that's our percent yield equation. Let's look at what we know and what we're trying to solve for. So it says, what is the percent yield for the reaction? So this is what I'm trying to solve for. Which means that I need the actual yield and the theoretical yield. Well, it says here that I have recovered 12.5 grams of NH3. So that's going to be the actual yield. So the actual yield of NH3 is 12.5 grams. What's the theoretical yield? Well, I don't know yet. But I would know the theoretical yield if I knew how much NH3 you could make from 4.70 grams of hydrogen and excess N2. Did I give a balanced equation for this reaction? I did. There we go. That'll help a little bit. Okay, so let's use the balanced equation to try and figure out what the theoretical yield is. I'm going to react a mass of H2, and the goal is to find a mass of ammonia using the balanced chemical equation. Well, like we said last week, first step is to convert everything into moles. And then we can convert from one mole to another using the balanced chemical equation that's right here. Okay, so let's look up masses in moles. So what is the mass of 1 mole of H2? Well, if we go to Lentech, I need those shape slides for later things. Or grab a periodic table, and I'll type in H2. So 1 mole H2 is equal to 2.016 grams H2. And I have the page on screen right now, so I might as well use it. So NH3 is 17 something, right? Yeah. 1 mole NH3, 17.03 grams NH3. And then finally, how many moles of H2 are there per moles of NH3? Well, according to the balanced chemical equation right here, every 3 hydrogen I use, I make 2 ammonia. So that will be my relationship. All right, I've got all my relationships figured out. Can I make the link for Lentech? Sure. There you go. Yeah, just bookmark that because you're going to use it so often. You don't want to have to go searching through my videos for the link if you've started your quiz and you're like, "Oh shit. What was that? Was it Lintech? Luntech? Losertech? I don't know." It's just the best one that I've used. Because everything's just right there. Alright, we're going to do our dimensional analysis here. I'm going to convert grams of hydrogen into moles of hydrogen. Just like our chart says, we're just going to follow the chart here. Then we'll turn moles of H2 into moles of ammonia. And then finally, we'll turn moles of ammonia into grams of ammonia. Now I have all the units in place. Let's run the numbers. So, relationship between grams and moles. 1 mole of hydrogen is 2.016 grams. 1 mole, 2.016 grams. 3 moles of hydrogen to 2 moles of ammonia. 3 moles of hydrogen, 2 moles of ammonia. 1 mole of ammonia is 17.03 grams ammonia. I need my calculator. And I got 26.468. I only get 3 sig figs, so we'll just call it 26.5 grams of ammonia. So now I can come up here and report that the theoretical yield of ammonia was 26.5, because that's what we calculated. So now we'll scroll back up to the top and we'll compute the percent yield. So the actual yield, what we really got, was 12.5 grams. What we were supposed to get in theory was 26.5 grams. Those cancel. Times 100%. And the value that I get was 47.2% yield. Now, if you look at that, your first instinct might be, wow, that's not very good. But it turns out that that's actually pretty normal. If a reaction does not go to 100% yield, who's to say it goes to 90 or even 60% yield? So there is no gradient for reactions in terms of, like, this is a good yield and this is a bad yield by just looking at the reaction. So for all we know, 47% could be like an extremely high yield. So don't look at percent yields and go, oh, this person obviously has no idea what they're doing if they only got a 47% yield. Because sometimes that's the best that you can do. All right. My answer is a little bit different, but that's okay. Ours was close enough. What was ours? Yeah, 47.2. Close enough. All right, let's do another one. I'm going to have you try this one. We're going to do this reaction. I'm going to put aluminum metal in a solution with copper 2 chloride, and I'm going to precipitate out copper. All right, so let's suppose that I use 96 grams. Well, it says she. Okay, so let's suppose that this chemist used 96 grams of aluminum and had an 87.7% yield. So what mass of copper did she recover? Well, I'm going to start you by giving you a hint. So let's write the percent yield formula. And then let's identify what terms we know. So we know her percent yield, so you know that number. And if you use this much aluminum, you could calculate the theoretical yield. So this question is asking what mass of copper was recovered. So you're going to solve for this actual yield. So first, find out what the theoretical yield is from 96 grams of aluminum. Actually, I guess first you should balance the equation because it's not balanced. Do the stoichiometry. Tell me what the theoretical yield is for copper. And then if you have 87.7% yield, tell me what the actual yield is. Okay? I'm going to give you about 5 minutes to play around with this. We'll go over the answers in just a bit. How are we doing? Let me know in the chat when you have the answer. All right, one more minute. We'll go over the answers. If you got an answer, go ahead and put it in the chat for me. All right, let's go over the answer here. So, just like before, we're going to need to calculate the theoretical yield. So let's go percent yield, actual over theoretical times 100%. So the theoretical yield would be, well, first we got to balance the equation. So I'm going to just balance it really quickly for you. So this is a 3, and this is a 2. So hopefully you got that first. That's an important place to start. Then we're going to take our 96 grams of aluminum here. And we need to turn the mass of aluminum into the mass of copper. So how do we do this? We'll first turn them both into moles. And then I can turn moles of one into moles of the other using the ratio from the equation we just did. All right, so let's look up the masses of these. So in a mole of aluminum, there are, where's my periodic table here? 26.982 grams. And in a mole of copper, there are 63.546 grams. And then the ratio of aluminum to copper here is, so moles of aluminum to moles of copper is 2 to 3. So 2 moles aluminum, 3 moles copper. Okay, let's do the stoichiometry. So grams to moles of aluminum, those cancel. Moles of aluminum to moles of copper, those cancel. Again, we're just following the chart here that we just made. Moles of copper, grams of copper. That's the unit that we want because that's the unit that will tell us the theoretical yield of copper. Now let's run the numbers. So 1 mole aluminum, 26.982. 1 mole, 26.982 grams. 2 moles aluminum to 3 moles of copper. So 2 moles aluminum, 3 moles of copper. And then finally, 1 mole of copper, 63.546 grams. 1 mole of copper, 63.546 grams. There you go. I just say them over and over to make sure that I'm putting them in the right spot. Now we'll punch it in the calculator. And I got 339.138, but I only get to keep 3 sig figs anyway. 339 grams of copper. So that's my theoretical yield. So if I go back to the formula up here, my theoretical yield would be 339 grams. My percent yield would be 87.7%. So all I gotta do is solve for actual yield. So we're gonna go down here and do that. So percent yield equals actual, So it's that. I'm going to solve for actual yield by multiplying both sides by theoretical yield. So I'd get this. And then I'll just divide by 100% to get this over there. So we'll take my theoretical yield. And I'm going to multiply by my percent yield, which was 87.7%, divided by 100%. The percent cancels out, and the actual yield was 339 times 87.7 divided by 100, which is 297 grams of copper. So with an 87.7% yield, this reaction would produce 297 grams of copper. All right. One more for you to do. Actually, two more for you to do. So here's the reaction for zinc and silver. If you take zinc and silver nitrate, you make zinc nitrate and silver metal. So you could precipitate out silver. The first problem there, adding 25 grams of zinc to silver nitrate gives 72% yield of silver. Or how much silver did you make? We literally just did that problem. So do that the same way that in the problem we just did. And then the bottom one is just a percent yield. I give you the actual yield. You can find the theoretical yield and then make the percent yield. Okay, so try these two problems. We'll go over the answers. These take a while, so I'll give you like 7 or 8 minutes to do it. We'll go over the answers in just a bit. All right, 1 or 2 more minutes, and then we will go over the answers. Well, you can't get over 100% yield for these problems. I do want to talk about what happens when you get over 100% yield in a second, though. Because in the laboratory, it's actually pretty possible. Due to some common errors that can occur. So let's go over these two problems here. So let's clear all this out here. I'm going to zoom this out a touch. There we go. All right, so first we got to balance the equation here. So we got zinc and silver nitrate makes zinc nitrate and silver. I'm just going to ignore the phases because whatever, right? So 2, 2. That should be right. All right, and so for number 1, we're going to add 25 grams of zinc. And we're going to get silver. So we'll do mass of zinc turns into mass of silver. Just like before, we're going to turn everything into moles. And then we'll turn moles of one into the moles of the other. Okay, and then we know that in 1 mole of zinc, there are, on the periodic table, it's like 60 something. 65.38 grams of zinc. Same for silver, we can look that one up too on the periodic table, 107.87. And then finally, for the ratio of moles of zinc to moles of silver, For every 1 zinc, I get 2 silver. Thanks to the balanced chemical equation that we got here. We'll do the stoichiometry. Grams of zinc becomes moles of zinc. Moles of zinc becomes moles of silver. And again, we're just going right down the list here. Moles of silver, grams of silver. Once we got all the units set up, we can run the numbers. 1 mole of zinc is 65.38 grams. 1 mole, 65.38 grams. 1 mole of zinc makes 2 moles of silver, so 1 zinc, 2 silver. There you go. 1 mole of silver is 107.87 grams. 1 mole, 107.87 grams. There we go. Punch it all in the calculator. What do we get? 25 times 2 times 107.87, 65.38. I have 82.5 grams of silver as the theoretical yield. Now we can use that to calculate the actual yield, which is the percent yield, 72.3%, and the theoretical yield, which is the number we just got, put together. So percent yield is actual over theoretical times 100%. So doing the algebra, that would be the theoretical yield times the percent yield over 100% would be the actual. And so that would be 82.5 grams times the percent yield, 72.3%, over 100%. Those units cancel. And I get 59.6 grams of silver is my actual yield. All right, that's the first one. Now for the second problem, we're doing the reaction with 30 grams of zinc and we get a different theoretical yield. So all I have to do for my problem is I just go up here and go, whoop, get rid of 25, whoop, and replace it with 30, right? It's the same problem, so this is going to change my answer. So 30 put into all this mess gives us 98.99, so 99.0. This is my theoretical yield for the second problem. None of this is useful, so we'll just trash that for this problem. But my percent yield would be actual over theoretical times 100%, which would be, well, she actually recovered 72.6 grams of silver. In theory, he should have got 99 grams of silver times 100%. These units cancel. And I get 73.3% yield. Ah! Sorry about that. I didn't mean to drag the screen off. I was just trying to underline, and I accidentally clicked on the little bar at the bottom. All right, there you go. So those are some example problems invoking percent yield. Did you find your mistake? It sounds like you did. That's good. All right, so I believe that is the end of the unit, which means that we have the celebratory, this thing. Yay, there's only one more unit left, and we're going to start that after the break. So let me put the... That's not right. That's right. There we go. Let me put this on here. We'll get more Persona 4 music playing. You just have the calculation back. That's okay. As long as you identify your mistake, that's what's important. All right. There is one more unit left. We're going to start that after this break. See you in a bit.
victory, but they fight all the place in it. Yeah, they fight all the place in it. Honey, times they just have the love goes by. I know it's not what you say, but there ain't no other way. So step on up to the plate. Need your faith, we can spread on into the light of love. Step on up to the plate, 'cause this ain't a game. It's time to make history, yeah.
Oh, look at that! I hit the button and then I immediately was just, like, working on something else here. Landed right on 10 minutes. Hooray! I mean, fortunately I have this track just right here. All right, let's do the last unit. So I'm going to talk about a little bit about solubility. I don't know if I'm going to get to the lab stuff today. We're just going to do the first two sections, and then we'll stop early if we have to. The concentration section, which is 16.3 and then 16.4, we're going to do that tomorrow during the lab section. And then the last day will just be, we'll work on problems from the last section. And if we have time, which we will, we could do problems from the lab so that you could see how to do that. So, let's see here. All right. Oh, this might be my really, really bad video. Oh, no, I found a better one. Okay, good. When I say really bad video, I don't mean a video that I made. The video I found was made by a student. Very clearly, like a student in high school. Like, this was their project. I hit the wrong button, didn't I? Okay, well. I have to resize this, but that's okay. Alright, so what happens when you put sugar in water? So here are some cups. We'll just cover up the chat for now. On the left, I believe, is hot water, and on the right is cold water. I might have that mixed up. Let's see here. You can see that just dropping these sugar cubes into the water, like, they start releasing bubbles from them. That's not a chemical reaction happening. That's just air that's trapped inside the sugar crystal that's being freed as the sugar starts to dissolve. Now, the one on the left is obviously going much faster because the water is warmer. But slowly, bit by bit, the sugar on the crystal is dissolving into the solution. And this video is apparently 3 minutes long, and I'm not going to make you sit through that. Oh. As soon as I hit stop, it started to dissolve, like, appreciably, and it looked kind of cool, so good job timing that one out. Alright, so when something begins to dissolve, it will break apart into the solution into individual units. We would describe anything that does this as soluble. So sugar is soluble in water. It will dissolve. Something that doesn't dissolve would be insoluble. This would be something like dirt. If you try to dissolve like a rock or mud into water, a little tiny bit of it dissolves, but most of it just settles to the bottom. Those compounds are insoluble. They do not dissolve in water. Now, there is a range between soluble and insoluble. This is not a black or white scale. Instead, it is sort of a gradient where you can have something be like slightly soluble where it's mostly insoluble but a little bit dissolves. And even when we use the word insoluble does not mean zero dissolves. It means that a very small amount dissolves. When you get to 163, we talk about solubility products, and we look at compounds that we consider insoluble. Oh, excuse me. And we find that the amount that dissolves is on the order of like 10 to the minus 5 grams or something like that. It's really tiny. Now, when you put two things together, you make a solution. The two things have to be something you're mixing and something that you're mixing it into. All you need are two substances to make a solution. You cannot have a solution if there's only one thing. You have to mix two things together. The solute is the substance that there is less of. And the solvent is what there is more of. You dissolve the solute into the solvent. Now, once you've done that, you will have a mixture. If you mix it thoroughly, you will get a homogeneous mixture if the compound is soluble. If the compound is insoluble, you get a heterogeneous mixture because it will just settle to the bottom. Now, it's easy to think, oh, okay, if I'm making a solution, I must be using water or some other liquid as my solvent. But it turns out that everything can be a solution in any combination of phases you want. For example, if you take a deep breath, air is a solution. The solute in air is oxygen or water vapor or carbon dioxide or whatever, and the solvent is nitrogen. Nitrogen is the most common substance in the air. For solutions that are in the liquid phase, generally the solvent is water. And you can dissolve all sorts of stuff in water. You can dissolve carbon dioxide, which gives you fizzy soda, like I'm drinking right now. Or seltzer water, I should say. It's not really fizzy soda. You could dissolve other liquid substances in there. For example, if you dissolved alcohol, you get booze. That I'm not drinking right now because I would not be able to teach. I'd fall asleep. Or you could dissolve solids. So you could do sugar to make sugar water. Or you could dissolve salt to make salt water. Or you could dissolve any number of solids in water to get various things that you may or may not want to eat. I'm thinking of food because it's almost dinner time and I'm hungry. Then finally, you can have some unusual solutions where you have solids as the solvent. And for these solids, typically what happens is to make the solution, you have to heat it up until it's molten. And then when you cool it down, it's in the solid state, but it's still a solution. So for instance, when you make an alloy, such as electrum is a mixture of silver and gold. The way that you do that is you melt silver and melt gold and pour them into a container in whatever ratio it is that you want. You make the electrum alloy, and then the result is a solution, even though both components are solids. Mercury is really insidious. It can get into metals very easily by just forming metallic bonds and then working its way in. So if you get mercury on a metal, it will eventually seep into that metal. And the only way to really get it out is to heat the hell out of it until the mercury literally boils out, which is kind of creepy to watch, but it's also kind of cool. And then I don't know how you would bubble hydrogen into palladium metal other than making the solid molten. But you can totally do all these things. And they're all solutions, because they're just mixtures. For every substance that you can dissolve in a solvent, there is a solubility that is associated with it, and that solubility changes with temperature. Most of the time, the solubility increases, as you can see on this chart here. Now, this chart shows the solubility of just some substances that are just chosen. But there are a ton of different solutions that have been measured already. And so let's just pop this on the screen here really quickly. This is the solubility table for various substances. And you can see this is just A. These are substances that start with the letter A. This is how many grams you can dissolve in 100 milliliters of water. So for aluminum fluoride, you can, if I hover over them, you get like pictures and crystal structures and stuff like that. So aluminum fluoride, you can dissolve half a gram of it at 0, 0.7 at 30 degrees Celsius, and at boiling water temperature, you can dissolve 1.72. Whereas with ammonia, you can dissolve 1,176 grams at 0 degrees Celsius, but only 88 at 100. Now, that's interesting that ammonia gets way less soluble, and we'll talk about why that is. It turns out it's because ammonia is a gas. The rest of these are all solids. Gases have solubility that goes down as temperature goes up, but most solids increase in solubility. And you can see that for all of these examples, that the solubility tends to go up as we go left or right. Like ammonium nitrate, pretty soluble at 0, extremely soluble at boiling point. You can put almost a kilogram of it into a milliliter of water. It'll just soaks it right up. And there are a lot of substances out there. So if you need solubility data, look on Wikipedia. It's probably there. And maybe, I don't know, if you want to contribute to a body of science, you could do the experiment. Nobody's determined the solubility of zinc nitrate at 10 degrees. That seems like a pretty easy one for you to get. Just put it in the freezer until it's cold enough. You could just do the one at room temperature. Like, that's low-hanging fruit, right? If you want to get your foot in the science door. I'm pretty sure that if you wrote on your science resume that, yeah, I provided the 20 degrees Celsius solubility of zinc nitrate, nobody would really care. But it's cool, right? So as we saw, most cases, solubility increased. Some solid solubility decreases. This has to do with entropy and thermodynamics. We'll talk about that in 162. But for now, it's just most of them go up. They go up at different rates. But we can do some interesting things. Hold on. Sorry, I just want to... Oh, it's back. It's here where I'm going to talk about that. We can do some interesting things if we can play around with the temperature and how much is in solution. We'll talk about that when we get to supersaturated versus saturated and unsaturated. All right. Your text uses these thresholds. I think that they're stupid. I really don't care about slightly soluble. Generally speaking, we're going to just categorize something as insoluble if very little of it dissolves, and soluble if lots of it dissolves. And it should be pretty obvious which category is which. If you pour something into your solution and you stir it around and it doesn't dissolve within 5 minutes appreciably, it's insoluble. But if you pour it in there and you just have to mix it a little bit and give it some time, it's soluble. So I will leave these numbers here just in case you see problems related to them in this class or future ones. But personally, I think that the most common by far are going to be insoluble or soluble. It's very rare that you see slightly soluble. Now, even if something is soluble, there is a limit to how much you can dissolve in a given volume of water. So, for example, this is copper sulfate. Copper sulfate is quite soluble in water, and you can tell because the solid is blue at the bottom, and up at the top when I look in the liquid layer, it's also blue. At some point, though, all of the solid will dissolve that the solution can hold. What that actually means, and this is what's happening in the solution, is that things dissolve at a certain speed. And that speed's going to be relative to the amount of water that's available up here for it to dissolve into. But at the same time, once I fill this with stuff that is dissolved, so this is all my copper sulfate, eventually it will bonk back down and start to find this again, and it will recrystallize. And depending on the amount of solid that's up here, at some point it will start to recrystallize at the same speed that it's dissolving, and you reach an equilibrium. And it looks like, oh, the solid is not dissolving anymore. It's reached the maximum. That's it. No more people can come into the solution, right? But in reality, people are just going in and out, people being ions in this case. It's kind of like an amusement park where at some point in the day, you reach the maximum number of people that are in the park. But it's not that people stopped coming in or leaving. It's that the number of people entering and exiting is the same number. Like every minute, 20 people enter and 20 people leave because they're done for the day while other people are coming in. So the amount that's there remains constant. And so that's what we mean by, oh, you cannot dissolve anymore. It's reached the maximum. We call a solution like this a saturated solution. Saturated solutions have everything they can hold because any more dissolves into it, it'll just immediately come out of solution and undissolve. Now, if you have less than this amount, the solution that you get is called unsaturated. An unsaturated solution can dissolve more. If you put solid into your solution and it dissolves completely, there's nothing down here for it to recrystallize to. And so recrystallization doesn't occur, and you just get something that's dissolved in there. But that can only happen if there's only a little amount of solute in there. Now, you can look at a solution just based on its color and say, oh, well, this one is darker. I don't know where my cursor is. Where did it go? There it is. Okay. This one is darker than this one down here. So therefore, the solution on the top picture must be more saturated than the one on the bottom, because more color is shown. This has to do with the optical nature of solutions. Light passing through a solution will be absorbed by the solute. And then, depending on what light is absorbed, the remaining light passes through to your eyes and you observe a color. Not the color that's absorbed, because that light doesn't make it to you. You get the complement of that color. Now, looking at this chart here, we can make some analysis, and I'm going to start by looking at this KNO3 graph right here. I'm going to look at these 2 points here. So if I put 20 grams of KNO3 in 100 milliliters, which is 100 grams of water, at 20 degrees Celsius, if I'm right on this line, I have dissolved as much as I possibly can, and if I try and add any more to this, only this much will dissolve. So this would be a saturated solution. Now my question for you is, what would happen if I prepared a solution of 20 grams of KNO3? Apparently it's 30. I can't read the damn chart. Sorry about that. So I'm looking at this axis. I was looking at the wrong axis. Oh, and I wrote it for both numbers. I'm just dumb. Okay. All right. So 30 grams dissolves in 100 mils of water at 20 degrees Celsius. That makes a saturated solution. But now what I want to do is I want to heat this solution. If I heat the solution, what happens to the solubility? Is it still saturated, or does it become unsaturated? Well, if I heat it, my solution state is going to move in this direction. So we'll say we heat it to 50. And this is where it is. Ignore the K2CR207 line. What state is my solution in now if I have heated it with 30 grams in it? Is it saturated or unsaturated or whatever? What's the result? Any idea? Very good. It would be unsaturated. Why? Because at this temperature, I could, in theory, have this much in there, right? But I only have 30 grams instead of 90. So solubility increases with increasing temperature. I could dissolve more, but if I just heat it up and that's all I do, the solution is now unsaturated. Okay, now what we're going to do is we're going to work backwards. We're going to start up here. So this is about 85 or so. And this is at 50 degrees Celsius. And this solution would be saturated. Now I'm going to do something interesting. We're going to allow the solution to cool. That O got away from me and became a B. So I'm going to allow the solution to cool to, say, here. Now, what happens and then what visually will appear is kind of difficult to predict. I mean, what happens should be pretty straightforward. What type of solution is this? Well, if it was unsaturated when it had too little in it, and now I'm on this side of the line, what would I call this solution? Give you a hint, it's right there at the title. I'm just imagining somebody is going to say it very soon, so I'm going to just start writing it. So this would be a supersaturated solution if I allowed this to cool down, because solubility decreases as temperature goes down. Well, if I've already dissolved 85 grams in there, it's still dissolved, right? Now, this goes back to what I showed you on the previous slide right here, where if everything is dissolved in my solution, it can't recrystallize down here because there is no crystal to attach to. In this case, it's the same. I have a solution that is extremely concentrated because I have dissolved all sorts of stuff in it. But in order for it to crystallize back into a solid, there needs to be a place for it to start collecting. These ions are very tiny, and the odds of them finding enough of each other to stick and form a solid are not very high. Any two ions bunk into each other, they might be attracted to each other, but water is also attracted to them too. You need a bunch of ions to start collecting in order to exclude water. So as the solution cools, nothing undissolves. You might think that, oh, instead it should just do this, right? And then whatever temperature it stops at, it'll just immediately crystallize stuff out. And it would like to do that, so your intuition is right. But if it doesn't have a way to initiate the crystallization, it can't. And so during that time, our solution is supersaturated. So what we're going to do is we're going to show what a supersaturated solution looks like before crystallization has occurred and then after. Because you've seen how to make it. It's very easy to make a supersaturated solution. Just dissolve everything and then cool the solution down in a container that is very, very smooth. So here we're going to show sodium acetate. Oh, good, that's set to the right side. Now, if you look very carefully, you can see the instructor. In his hand right here is a container with sodium acetate, and he's going to put that onto a little spatula and then put it inside this flask. The flask contains dissolved sodium acetate. And so here we go. So there's the tip of the spatula with the crystal in it. And then when I hit play here, this is what happens to the solution. So you can see that this crystallizes really fast because there was just so much in the solution and it was all dissolved. But crystallization cannot occur if there's no place to initiate it. So it's hard for stuff to crystallize randomly. But if you provide a spot for it to happen, it will happen very, very, very quickly. Now, I do have another video to show of this, so let me see if I can find fun with sodium acetate here. Oh, where's the specific video? It'd be really sad if they took it offline here. Nope, there it is right there. Alright, so here's some fun with sodium acetate. It's so supersaturated that it crystallizes so quickly, and you can initiate this by doing any number of crazy things to it. So yeah, this is like rock candy, except rock candy uses sugar, where you make a solution of sugar and then you put a string in it, and the sugar crystallizes on the string. So this is exactly rock candy, yeah. Now, this person's demonstrating that it makes a solution that is actually really firm. There is water still in here, and when they break it apart, you could see on the surfaces that there's like glistening parts to it. That's the water that's now trapped in the solution. Now, it's dissolved, and it makes a structure that has a much lower density. So that's why they're pouring these drops on there, and it seems to be expanding to something that's way larger than the volume that they poured out. Now, if you aren't careful, this happens. Oops. Do. Now, you can see that it tried to start crystallizing on its own there. That's uncommon. Normally, you have to help it. What this person is doing is dipping their finger in a bit of sodium acetate crystal to facilitate the crystallization. The end. There you go. All right. So those are the three types of solutions that we can have. We can have unsaturated, saturated, and supersaturated. Supersaturated, not very common. You're not going to see it all that often, but just be aware that it does exist. Saturated is the most common when you're making solutions. You'll eventually get to the point where, oops, no more dissolves. For the laboratory, you will want to be working with things that are unsaturated only by virtue of an unsaturated solution won't change its concentration over time. It will just remain constant because there is no extra solute to dissolve into it. And then finally, solutions are made out of any two things that you want. We're going to be working with aqueous solutions in this class for the last unit. But in 161 through 163, you're going to be working with water as the solvent. And it won't be until you get to 261 where you see anything else as the solvent. All right, so I'm going to give you an example solution here. I don't care about the second question, so I'm just going to cover it up there. Actually, no, we've already talked about this. Which of these is the solute? Well, it's the one that there's the most of. It's nitrogen. The rest are solvents. All right, so that's our crash course on solutions and solubility. The last thing that we're going to do today, if we have time, let me see what time it is. Oh, I have time. Okay. We're going to talk about solubility rules. Now, the solubility rules are not really rules so much as they are guidelines, because most things follow these rules, but there are always exceptions, and memorizing what's soluble in water and what's not is really not easy to do. So what we do is we give you a table, and I'm just going to test you on your ability to use the table. Okay? Now, what this means is that depending on what application you're looking at, you're going to have to know to look back at this table and say, oh, I should refer to see if this is soluble or not, because not everything will be soluble. And if it is soluble, you might want to do something with it. And if it's insoluble, you might not be able to do that thing with it. Okay? So remember where this table is. I always provide this table with my exams, but because this is an online class, you can just look this up. Here's the solubility rules. There are more of these rules online that have more or sometimes fewer, I guess, descriptions. These are the ones that I care about for this class. The way that you read this table is they're going to split it into two sections. We've got the soluble section, which is this one. And then we've got the insoluble section, which is this one. So if I give you a compound, and I'm going to just write down a random compound here. So let's say BaCl2. What you're going to do is you're going to first split this into the ions that it can be made from. So we got barium 2 plus and chloride minus. You don't have to balance it. We just want to know what ions there are. And then what you're going to do is you're going to look for these ions in the chart. So let's look for barium. Is barium anywhere in here? No. It's not there. So let's look for chloride. There's chloride. So chloride is soluble unless it is partnered with one of these things. Since barium is not one of those two of those things that is listed there, barium chloride would be soluble. So that's how we would use this chart. Oops, I didn't mean to go backwards. I meant to erase. Let's do another one. So now let's do iron hydroxide. So we would split this into the ions that make it up. And now we look in the chart. So I don't see iron in here, but I do see hydroxide. All hydroxides are insoluble unless they're paired with one of these things. Well, iron is not one of these things, so this would be insoluble. Now, if you do land on an exception, then you are the opposite of what table you're in. So, for example, if I looked up AgCl, which is these ions, I would look up chloride and say, oh, chlorides are soluble unless they're paired with Ag+, which we do have, so this would be insoluble. All right, that's how you do the solubility rules. We're going to come back to that in just a second. Now, why do things dissolve in water? Things dissolve in water because water has a property called polarity. We don't talk about polarity in 140. We talk about it in 161. What polarity is polarity is like something is ionic, but partially. So water has so many more electrons on this side of the molecule than it does on this side that it's almost like it has partial negative charges on it, and the other side would be partially positive. Now, if I have something that's partially negative, it's going to be attracted to something that has a positive charge. That includes metal cations. So you can see that in the structure at the top there, the water molecules, all of their oxygen oriented toward the sodium ion. Likewise, in an anion where I have a negative present, the positive part of water will align itself towards that. And because these are interactions that can extend in all directions, the sum of all of these interactions ends up being stronger than the ionic bond between these two. And so the ionic bond splits apart. When there's lots of water, the water can carry these ions away. And this property of water is called polarity. Water is polar. Now, because water is I read the next word there. Because water is polar, it will also interact with other things that are polar. For instance, vinegar is polar, or acetone is polar, or ethanol is polar. But oil, it turns out, is nonpolar. Oil doesn't exhibit these properties. If you mix oil and water together, they don't interact. We're going to talk about that in a lot more detail in 161, and again in organic chemistry. But for our solubility rules, what we care about is, one, we want to consider, does something soluble Is something soluble because it says so on the solubility table? Or number 2, is something soluble because it is polar and the solvent is polar? So the rule here is called like dissolves like. Water will dissolve polar things, but it will not dissolve nonpolar things. 2 nonpolar things will dissolve into each other, though. So, for example, if I take acetone, which is polar, water, which is polar, and I mix them together, will they be soluble? Well, like dissolves like, so yes, they will dissolve in each other. You can pour acetone into water all day. You will not make a second layer, they will not separate. What about cooking oil? Cooking oil is nonpolar. Will it mix with this other random nonpolar thing that I found online? Yeah, they're both nonpolar. All right. What about these solids? We already did barium chloride. How about calcium carbonate? So let's go back to our solubility chart, which means I got to go all the way back here. And we'll look up calcium carbonate. So I'll give you a second to think about this. Split this into the 2 ions that it makes. Look for those ions in the chart and then tell me polar, or not polar, I'm sorry. Tell me soluble or insoluble in water. Then I'll just go look up what the next ones are so that we can do the examples here. Alright, so hopefully you've written down that these are the 2 ions that are made, calcium and then carbonate. So let's look for them. Is calcium in this chart? No. Is carbonate in the chart? Yeah, it's right here. So here's my carbonate. Carbonates are insoluble unless they are paired with something from group 1A or are paired with ammonium. Well, this is not one of those things, so this would be insoluble. And then what was the last one that I had there? Let me check real quick. Ammonium phosphate. So now what we'll do is we'll look at ammonium phosphate here. What are the ions that this splits into? And is it soluble or insoluble? I'll give you a second to think about it. All right, so ammonium phosphate should split into ammonium and phosphate. Now you just got to find those. So where's phosphate? Oh, here's phosphate. Oh, here's ammonium, though. We've got both of them on there, and they're in different parts? How the hell is this going to work? Well, they'll lead you to the same answer. So anything paired with ammonium is soluble, no exceptions. So we should get the same result down here. Phosphates are insoluble unless paired with group 1A or ammonium. And it totally is. So if you find something on the chart, use that and you'll be good. If you find the other thing on there, it should point you to the same answer. Otherwise, there's an issue with the chart. All right. So for our examples here, what I want you to do is tell me, will the first thing is the solute, will it be soluble in the second thing, which is the solvent? Okay. For the first two substances, I just want you to use the polarity. Remember, like dissolves like, so tell me if it's soluble or insoluble. And then for the other ones, tell me if the ionic compound will dissolve in those things, or will dissolve in water based on the solubility chart. You'll have to go back to the solubility chart, which means you might have to rewind the video a little bit, or look at your slides in your notes. Okay? So I'll give you 5 minutes to do that, and then we'll go over the answers, and then we'll call it a day. All right, one more minute, we'll go over the answers. All right, so for the first two, we're going to just look at the polarity based on what I've told you. And we'll go like dissolves like, so these two are the same. They're both nonpolar, so this will be soluble. However, oxygen is nonpolar and water is polar, so we would predict that it would be insoluble, and that's actually true. The solubility of oxygen and water is extremely low. And that is both good and not great for certain life forms. So there is lots of oxygen in the atmosphere. About 20% of our atmosphere is oxygen. But if it was more soluble in water, all of that oxygen would then get absorbed into the ocean. And so we would all suffocate and die on the land. However, that being said, then there would be far more oxygen available in the water, and then life would flourish in the water. So fish are very low oxygen creatures in general. I mean, they need oxygen to survive, but there's not very much of it in the water, and so they have to move very quickly through water to get what little is dissolved in there. For the rest of these, we want to look at the solubility chart, except for the last one, which is special. So let me go back to the solubility chart here. We'll clear this, and then I'll go print screen, and we'll put it in this thing. There you go. So now I can just do this, and we can refer to it really quick. Oops, hold on. There we go. All right, so we'll look at the first one. So sodium nitrate in water. Is it soluble? Well, the ions that splits into are... Oops, I got to write it on this one. I'm writing on the wrong thing. So we get sodium and then nitrate, and both of those are in the soluble category with no exceptions. So this is soluble. It's very soluble, actually. Will potassium sulfide dissolve? So I got K plus and S2 minus. Now, if you look on the chart here, I don't have the pen selected. Sulfides are insoluble unless they're paired with group 1A, which is potassium. So therefore, this is soluble. If I look at PbCl2, these are the ions it is formed from. And if we go to the solubility chart, I see that chlorides are soluble unless they're paired with these substances, which includes lead here. So therefore, PbCl2 would be insoluble. For barium hydroxide, here's my barium and my hydroxide. Hydroxides are insoluble. You can see at the very bottom of the chart there. However, paired with barium is an exception, so that would be soluble. There you go. There's our solubility. Now this last compound down here I'm going to give you the answer. Whoops. I ran off of the screen here. There we go. I'm going to give you the answer, and then we'll explain it. Why would salt not dissociate in benzene or dissolve? Well, we set up here, benzene is nonpolar, right? So if benzene is nonpolar, and like dissolves like, remember that salt, table salt is ionic. Ionic means has charges. Nonpolar means no charges. So they won't dissolve. No ionic compounds dissolve in benzene. Or I should say ionic solids. All right, I believe that, yep, that's all we're going to do today. We're going to come back tomorrow for lecture. We're going to start by talking about concentration and molarity. And then we'll talk about how to dilute stuff, and then we will show how to do the experiment on the lab paper. Okay, because the last lab, it's just basically this chapter and a little bit of the previous chapter as a concept check. And we're going to talk about this technique called titration, and it's pretty neat to see it in action, to see how we would do the reaction. I much would prefer that we could do it in lab, but unfortunately, it's not in the cards. So, all right, I do want to thank everybody for coming out to the lecture. Tomorrow will be the last lab discussion and Q&A, so make sure you bring questions to Q&A if you have them. And it will also be the second to last time that we meet. So we have Wednesday and Thursday, and then we're done. So the exams will come up shortly after that. Have a wonderful rest of your evening, and I'll see you tomorrow.